In the previous video in this series, in which I am attempting to restore this LRP-300 paper tape punch and reader, I got as far as starting to fault find on the main PCB. We found a fault with the drive for the tape advanced stepper, and so I corrected that. It was just a failed IC, and so in this video we'll continue with this fault finding. So the next thing I want to look at is the control for the paper tape punch. I don't know if you can actually see the LEDs on the display board or not. I'll power it up, and the LED for the punch is actually on, but nothing happens when I press the switch. It just stays on. And so I'll attack this in the same way as I did with the previous fault. So we'll start with the control board itself. And I want to look to see if this line here, it's labelled punch on clock, and we should be seeing this go high when the key is pressed. So that's pin 10 of U2, so that's this one. And this should go high when I press the key. And indeed, that is working. So again, we can start looking at the main PCB, and this is the section in the PCB that controls this. We have this line here that says it's punch on LED, so that's what's driving this LED, so we know something in here is amiss. Now of course there are control lines coming into this that are used to automatically switch the punch on and off, because this can be controlled remotely. So there is logic in the main board that allows this function to be toggled remotely through the RS-232 interface. But we'll start by seeing what's going on here. This is where it's being driven from. So we've got a line going up here, but that's it's an input to this device. So what I'll do here is look at this pin. This is the output that drives the line that drives the punch on LED. This is a 7474, so it's basically it's a flip-flop. And what we can do is check the clock. The clock line comes from the toggle for the key, so that's the punch on clock that we just looked at. And there's a bit of a filter on the input to take out the noise, and then this should just essentially toggle each time we press the key, although it is preloadable based on some other functions that are going on within the punch, and this is what allows this to be controlled remotely. So we'll check to see what the status is around here. I won't keep showing you the data sheets. If you want to look them up, you'll be able to find them online. You're probably familiar with these devices anyway, but we'll start by seeing what the clock line's doing, the clear, the preload and the data, and that will tell us what we should be seeing on the Q and the not Q outputs, and we'll see if this device is doing what it's supposed to. So I'll power the punch back up. This is device A17, which is down here on the bottom row, so it's this device. And if we look at the clock pin to start with, that's the one from the key. So that's this pin, and if I press the key, we should see that line toggling, and we can see that that's working. So we'll look at the output and see if that's changing state. I don't think it is, because the LED is staying on, but we'll just check it next anyway, and that is pin 9. As we can see, that's not changing. Doesn't necessarily mean this is the faulty device. It depends on the signals going into it. So we know it's getting a clock. We'll check the clear line. So that should be 13. And that is doing what it's supposed to. So next thing to check is the data line. And that's low, so it should be clocking through a low value, unless the preload is trying to preload it to a high. So that's pin 10. And yeah, that should be high. So okay, it's been told to set Q high. So if we follow this back, that comes from IC B19. That's a NOR gate. So if we check this NOR gate and see if that's working, so that is, what did I say it was, B19. B19, so that's this one. So we're looking at pin 4, which is low, pin 5 and 6. So one of those must be high. And in fact, they are both low. So in other words, that IC is failed. So as before, I'll swap this out. I'll put an IC socket in and just double check that it has failed, and we'll retest it and see if that fixes this particular problem. Okay, I've replaced that IC. We'll power it back up and see if the problem still persists. So it's meant to come up with the punch in the on state, but it should go out when I hit this key, and indeed it is now going out, so that's toggling fine. We'll just double check that with the scope. So we want to look at pin 8 on this particular IC, and this line should toggle when we each time we hit this key, and as we can see, that's working fine. So the next thing I'm going to do is start to investigate the punch pin control circuit. If you recall, all the pins were being continuously energized, so it was driving all the pins up every single time. That may be related to the problem we were seeing. It was certainly the reason the punch was driven all the time, and it might be as simple as because it thought the punch was supposed to be running all the time, that it thought it was supposed to be punching the data that was in the data buffer. But of course, without any data having actually been received, then there wasn't really any data to punch, so that might be why it was doing that. But I'll try looking at that next. We'll see what the state of those pin control lines is. So I'll grab the relevant sheet in the schematic and we'll continue this investigation. Okay, I was going to test the functionality of the punch head at this point, but decided to test a few other parts of the circuit first. In particular, I want to test this block up here, and the reason I've decided to do this first is when you're dealing with something like this, it doesn't really matter the order that you fault find in, although it does make it easier if certain parts of the system work that are required when testing something else. So this looks quite complex, but all it really is a sine drive control for the tape advance stepper. Now, if you've seen my videos on other tape punches, then I've mentioned previously that the tape has to be accelerated and decelerated relatively slowly to stop the hole in the tape being snagged so it doesn't tear the tape, and so it's properly handling the tape. You can't just suddenly apply a huge force to the tape. It's not very heavy, but it's very easy to tear. And also controlling the rate at which the tape is accelerated and decelerated as it passes through the punch head means that you're going to get much more even spacing of the rows of punched holes, which is of course what this is for. Now, on top of this, these machines tend to punch relatively quickly. This only goes up to 300 baud, so it's 30 characters a second in effect, but even so it's still a fairly rapid rate of punching. And this particular stepper motor, the way this is arranged, is it's actually 4 steps for each row of holes. So it's essentially quarter stepping. It requires 4 pulses to move one entire row of holes each time it advances. So each time the feed or the backup space key is pressed, then it effectively moves all 4 steps. So the 4-phase stepper drive goes through a complete cycle each time it steps onto the next row. And in order to provide the sine drive in this particular machine, I've shown in previous machines, sometimes it's a mechanical sine drive linkage, and in this particular machine it's done through a series of timers for the individual stepper motor steps. So I'll do a quick sketch of what we're trying to achieve. So rather than moving the tape in this manner where it's a sudden step change in speed, so if this is time and this is speed, we don't want to suddenly change the speed of the tape. So what we're trying to do is achieve something a bit more like this. And so the way this system works is, as I say, there are 4 steps per row of holes in the tape. So the initial step occurs here, the motor starts to accelerate, and then there's another step here, another one here, and then a final one up here. So they're not evenly spaced, and the relative spacing of these pulses will determine this slope that we're trying to achieve. So if you're familiar with driving stepper motors, you'll know if you want to move them very quickly, you have to ramp up the step rate. You start off with a slow step rate, ramp it up, and then fairly quickly, over a few milliseconds, you can get it up to full speed, so the motor shaft momentum keeps the motor turning as the step rate increases. Now, of course, we can't do that with this system because the tape has to come to a complete standstill in order to allow the punch head to punch the holes. If it tried to do that while the tape was still moving, then most likely it would jam the pin, so the pin wouldn't be able to retract because the tape will have kind of moved slightly as the hole was punched. So the tape has to come to a complete standstill, the holes are punched, and then it has to quickly move and then come to another standstill for the next row to be punched. But we need this nice sine function to give us the acceleration and deceleration rate for the paper. So that is where these 3 timers come in. We have the start pulse, which doesn't need a timer, of course, because it's just the beginning of the cycle. But what it does is it triggers these 3 timers. These are just 555 timers in effect in a quad package. But it triggers them all at the same time. And what this causes is the 3 timers all have different time constants because of the value of the components that are used to provide their relative timing. And this is adjustable with 3 pots, and that's these 3 pots on the board, so you can actually adjust the profile of the acceleration and deceleration curve. So what I want to do now is just test that these 3 timers are working. So the first one should give us a pulse width of 3.4 milliseconds. So we'll get the scope and we'll see if it's actually working. So I'll power the punch back up. Okay, so we're looking for D12 pin 16, which is this device here, pin 16. We'll do a single shot capture, and we should see a pulse width of about 3.9 milliseconds. Okay, so we'll just measure that. I'll just adjust the cursors. And that's giving us 3.7 milliseconds, which is close enough. The next one should be 6.9 milliseconds, and that's pin 9 of the same device. I'll rearm the scope. Move the cursors, and as I say, we're looking for 6.9 milliseconds, and it's just slightly over 7, so again that's close enough. And then finally 10.4 milliseconds, which is pin 8 of the same device. And that's giving us 10.6 milliseconds. So the 3 timers are working, so these 3 timers are fine. And then finally I'll just check that the actual output pulses are correct. So all this is doing is just creating a 20 microsecond pulse for each of these timed events. It just needs a short pulse to update the stepper drive. So we're looking for D14 pin 1, D14 pin 1 is here. So rearm the scope, we're looking for quite a short pulse here, so I'll adjust the time base and we'll step the motor. And we have a pulse there of 20 microseconds, spot on. So the next one is pin 8 of the same device. That's 20 microseconds again, and then finally pin 16 of the same device. Again, 20 microseconds. So this circuit is working fine. We know now that the pulses provided should be correct, and it means it's safe to load a piece of tape in here, and as the motor advances, it is going to advance properly. And it's not going to hopefully tear the paper or do any damage to the punch head. So I'll get some tape, we'll get it loaded up and see if we can successfully punch a leader with this. So feed the tape through. Then I should be able to now create a leader and get it to pull the tape through the punch. And so as you can see, it's punching holes, punching them quite evenly, and it's leaving a nice flat tape. So that's quite a good sign so far. And what I'll do next is actually connect it up to a terminal, and we'll see if we can send it any data. I don't know yet if this will accept data or if it's if the RS-232 is working, but that's the next step. And I can now also start testing the rest of the functionality of the machine to see if the UART works, if the data can be passed through to the drivers to drive the punch heads. This hole that's been punched is just a fixed function of the electronics, so it doesn't really prove that the UART or anything else is working. But that's the next thing to look at, and see if we can get any actual data going through to the tape. Okay, I've got the punch connected to the terminal program on the PC, and I've got it set up hopefully so that it will actually punch. And what I'll do now is get the punch started up. We'll feed out a leader, and then I'll send some data from the terminal program, and we'll see if there's any activity on the punch at all. As I say, I don't know if the UART even works or if there are other faults on here. I've got the scope hooked up to the data in line, so this is the data coming from the terminal program, so we should be able to see on the scope if there's data actually coming in. And we'll see what happens. So as I say, I'll feed a leader out first, and I'll try sending some data. Okay, as you can see, we've got data coming from the terminal program, so now we'll try turning on the printer and see if it actually prints anything. Okay, well, it looks like we have a partial success. I don't know if the data's correct. What I'll do next is send some test data to check the reliability of the punching. I can see we still have issues. The spacing is not even, it's not correct. That's not that surprising. We're still going to need to do some alignment and possibly set the timing for carriage returns. There's an adjustment on the back to give a delay for the carriage return to allow the punch to keep up. Of course it doesn't have a buffer. Let's turn this off. But it's looking like it is successfully feeding data through. I just now need to make sure that the data is correct. So in the next video what we'll do is set the machine up to send some proper test data, and then we'll start looking at properly aligning the punch head and checking the settings and the full functionality of the UART.